This activity is called branching out, and we're going to do a slight variation from the way that it's done in the book. The way that it's done in the book takes a little bit of time and requires a lot of resources. So we found a way that you can do it that's pretty fast and easy to do with your students. So what you'll need is just a piece of wax paper, some watercolor markers, the cheaper the better, a roasting pan, and a squirt bottle of water. So what you want to do is you want to take your wax paper and just ball it into a little bowl. And gently unfold it, make your topography, leave it a little crumpled in some areas. Put it in your pan and make sure you leave the whole thing in the pan because we're going to be squirting water on it. Next, you take your watercolor markers, and we'll need a bunch of different colors. And you want to color some of the high points in different colors. And at first it's going to look like nothing's happening because these water markers don't really show up that much, but that's actually a good thing because once we squirt water on them, the color is going to bead up. So if it doesn't look like you're doing much, don't worry about it. So what do we know about water? Does water flow uphill or downhill?
Downhill.
Right. So where would we expect to find water in this model? On the tops of the peaks?
Down in the valleys.
Down in the valleys between the peaks. So you take your water bottle, you squirt, and you see how it's starting to bead up now? You can see why you would want to use watercolors. If you use any other kind of markers, this doesn't work. And you want to make it rain all over everything until the colors run. And you can actually see where the water would flow to in our little model here. And if the tops are what we would call ridge lines of a watershed, if you think of a watershed like a big bowl or a big bathtub, it would be the edges of the bathtub where the water will drain downhill from there. And so you can actually have one ridge line that is a part of two different watersheds. So if you look here, you can actually see where the purple and the orange met to make one. You can see where the orange and the blue met, and you can see what part of the ridge line went with which watersheds. So it's a pretty simple technique, and it's very fast, and it's pretty easy to clean up too.
Okay, so when Holly was working with you on the branching out activity, what you did was you created a three-dimensional river basin, right, of maybe multiple river basins in several cases, right? So what we want to learn next is how we take that 3D representation and we put it onto a two-dimensional surface. So if you would look at the end of the branching out activities, what you'll notice is that we have several different drainage patterns, and then you have a map of the North Carolina drainage patterns that you can see. Now, because of the fact that the geology basically drives the direction that the water will flow, because your softer rock's going to weather away a little bit faster and your water's going to drain down there a little bit differently than it would over your tougher rock, depending if it's igneous or metamorphic or sedimentary. When you look at that, you can see how there are 4 different major drainage patterns that are completely based upon the geology of that, wherever that stream may be found. So the most common one is which one, do you think? Yes, right. The dendritic is the most common one, and dendritic just means it's very tree-like, right? So, and on the previous page, you see how they kind of resemble it to the circulatory system in the human body, right? The one next to that is a radial drainage pattern, and where do you think you would find a radial drainage pattern? Right, top of the mountain, or you could actually find it at the bottom of a bowl as well, right? So radial drainage patterns can be in either place, and I think earlier on you did common water. That activity kind of shows you where you have a bunch of students around the basin and they're going to and from the basin in the middle, and you can actually see a great drainage pattern, radial drainage pattern from that activity if you just use the parking lot when you do that activity. On the bottom left, you'll see a rectangular drainage pattern, and that's the geology of that. You're going to basically be looking at really hard bedrock, bedrock that has very defined edges and planes. And the last one on the bottom right is your trellis pattern. And in this case, you're going to have two different types of rock. You're going to have an alternating pattern between your harder rock and your slightly easier to weather rock. So your streams are going to cut across in the slightly easier to weather pattern, and then you'll usually have one connector stream that kind of goes right up through the middle. And if you look at the North Carolina drainage pattern map, you can kind of see a few examples of these. This is all of the actual rivers and streams that you can see in North Carolina from above. If you look at High Point, you'll notice a great radial pattern right in there. If you look around Asheville, you should see a little bit of the trellis, which kind of makes sense because it's a mountainous area, you've got some valleys and peaks. The valleys are going to be where your softer rocks are, and the peaks are going to be where your harder rocks tend to be. And then if you look down south of Raleigh, if you look around just north of Wilmington, south of Raleigh, you may see a rectangular drainage pattern in there somewhere. They're a little bit harder to see sometimes. You may actually find some in this area in Raleigh because we do have a very large batholith, which is a very large, at least 100 square meters of granite that is an igneous intrusion that sits right up underneath Raleigh. So we'll probably get some rectangular drainage patterns here in Raleigh as well. Now, moving on from branching out, we're going to look next at how to understand topographic maps. How do we look at this three-dimensional river basin that you've created on a two-dimensional plane? So one of the things that I like to do with my students is I draw some circles to show kind of how contour lines work on a topographic map. So what you have here is that contour lines connect all the points of equal elevation, right? And it's a three-dimensional surface that I'm showing you here. And when you flatten your hand out, you can show how that three-dimensional surface could be projected onto a two-dimensional plane. You can also see with the knuckles how the water will drain in different ways depending on the hardness of the knuckle or the softness of the skin between. So you can kind of discuss with your students various drainage patterns that way as well. Okay? Now, each of you has a set of, I believe, 9 salad trays in front of you, correct? And what we're going to be doing next is sort of giving you a visual look at a very famous eruption, sort of a before and after shot. This is a really neat way to hammer home what contour lines mean to our students and to really kind of give you that visual to help kind of put this three-dimensional image together. So Mount St. Helens erupted in May of 1980. Massive eruption, probably the largest in the continental U.S. In recorded history. You could argue that Yellowstone was bigger before recorded time and all that. But what is so great about Mount St. Helens is that here you have this beautiful composite cone volcano, the stratovolcano, which means it has these alternating layers of lava and ash when it erupts. After the eruption, you see how, in this case, there are 4 instances that occurred when Mount St. Helens erupted. It started with a bulge on the north side of the mountain that was formed. You had an increase in earthquake and volcanic activity, and then you had a landslide that occurred because of this increase. The bulge kind of slid right down, I believe it was the north side of the mountain, and from that point, all that pressure was just building up in that volcano for all that time, just sort of, instead of going out the top like you would normally expect it to come out of in a volcano, just blew out the side of the mountain. And you can see the after on that picture. So what I'd like for you to do is take the left side of your salad tray so that the opened end is up and put it over the top of the before the eruption picture on the left side of your drawing. And we are going to do one contour line at a time. You can see that depending on the size of your tray, it could be a little bit awkward to start with 1300. So we're going to start with 1500 and work our way up the mountain. So all I would like you to do at this point is center it over the picture, and I want you to draw the 1500 line around your tray. Then what I'd like for you to do is you're going to move the tray over to the right a little bit and put it over the after and do the exact same topographic line. So you're going to do the 1500 line on this side as well. So after the 1500 contour line is done on both sides, what we're going to do is we're going to take the next tray and we're going to stick it on top of the other one, make sure that they line up perfectly there. Sometimes the trays, they get turned around and they kind of have a little bit more of a separation So make sure that they are fitting in nice and tight. And now we're going to do the 1700 line on the before and the after. So you color in the 1700, making sure everything is lined up. And the reason you want to stack the tray on top is because if you have each student do it separately, then when they put them all together, they're going to kind of go like this as you go up when you finally get the three-dimensional image. So you want them to go ahead and stack it up every time. Okay, 1700, and then we're going to work our way all the way up the mountain, one contour line at a time. And what you're going to finish with is a really great three-dimensional image of the before and after of the Mount St. Helens volcano. And what I really like about this is that not only can you see it, the three-dimensional image from above, but they can also turn it over and kind of like you're looking underneath inside the mountain. And as an earth science teacher, you can talk about, at this point, if you wanted to, you could add like where this is where the magma chamber might be, and this is where the vents could be found. And if you have one of the old projectors in your classroom, not the LCD kind, but the kind where you crank the acetate sheets all over, then you can put this on top and they can see the three-dimensional image. You can move it around and it can project it onto the screen. It's a really, really neat way of understanding what each contour line is measuring, how it, each one is that elevation. You can show them how the contour lines never cross. You can even show them how, when you look at it from above or below, the closer they are, the steeper the slope must be, and the farther apart they are, the more gentle and more gradual the slope must be. So it's a great way of explaining a lot of the most important aspects of a topographic map, including contour intervals. This naturally works with contour intervals, which is the elevation change between contour lines, because they're doing 1300 to 1500 to 1700, so they know they're going up 200 feet, in this case 200 feet every time, and that would be their contour interval. So there's a great many things that can be explained with this activity, and you get a really neat visual effect as well. Now that you've had an opportunity to see how the two-dimensional image of Mount St. Helens can relate to a three-dimensional viewing of that same drawing, what we're going to do next is look more in depth at what the two-dimensional topographic maps, what else they can show you besides, what the contour lines, the steepness of the slopes, and things like that. So, everybody should have a color printout of our wetland center here, where we're located. And if you look, you'll see right in the center of that picture is a little A. That is where the Walnut Creek Wetland Center is located. And you can see our stream is actually located in blue. Some of the things I want to point out to you on this map, first of all contour lines are in brown on official topographic maps. You'll notice that the salmon colored areas are going to be your cities or your urban areas. You'll see that the black is for your buildings, and blue, of course, is for your water. Green is for your forested or natural areas. And sometimes you'll see purple on there to show revisions on a map as well. Anything that's new since the original map was created. You'll notice, number one, first rule of contour lines is that they never cross. Right? Contour lines never cross, which should make sense, because you can't have two elevations in the same place. If you look towards the Raleigh city area in Salmon, you'll see how the contour lines start to get really close together below, and actually if you look at the top of the map, you'll see how the contour lines get close together. And that kind of shows you the steepness of the slope. And when you're explaining this to your students, one way that you can kind of think about this is if I have a pencil in my hand and this is, for example, 10 feet apart on a horizontal line straight across, this would be 10 feet away. But if I'm going down a steeper slope, you'll notice that the distance between my fingers gets less and less as the angle of the pen, in this case, changes. Okay? So that's one way that you can kind of visually show your students how contour lines can actually get closer together. Now, if you look in the green areas where we're located, you'll see that most of the contour lines in that area are actually fairly widely spaced. So you see this is a very gently sloping area, which means that not only, and plus if you look at the actual contour lines themselves, you'll notice that the elevation of those is lower than it is on the closely spaced lines above and below. So what that tells you is that this is a great place for water, which is a great place to put a wetland center. Walnut Creek, which the center is named after, runs west to east on our map. And you can see it follows in through those green natural areas, and you can see the wetland symbols as well on the topo map. Our study stream is Little Rock Creek, and it actually runs from north to south into Walnut Creek, right through Carthage Junior High School and right along next to our point in the middle of the map. The confluence, you can see where the two streams meet, and then they'll flow to the east and combine with the Neuse River. So that means that we are a part of the Neuse River Basin, which is the fourth largest river basin in North Carolina, very close to being tied for third, actually, with the Tar-Pamlico. And all of Wake County is, just about all of Wake County is in the Neuse. There is a small portion of it in the Cape Fear as well. Some of the other things I want to point out on the map, you'll notice that the roads kind of tend to follow where the highest areas of elevation are on your map. So if you look for any of the little circles, those are going to be your hills on a topographic map if it's an enclosed contour line. It could also be a bowl, but usually the way they'll delineate that on a topo map is they'll put little tiny tick marks that have it going towards the direction of, as it goes to the lower elevation. So inside an enclosed circle, you'll see some tick marks inside it, and that'll mean that it's a basin and not a hill on a topographic map. So you'll notice that the roadways tend to follow your higher levels of elevation. Okay? And what do you think you might find in the lowest levels of elevation? Besides water, what other things might you see in some of these areas? Farming, right? You'll see a lot of your more fertile land around your floodplains. That's really good because that flooding does provide the soil with the nutrients that you need to grow. You'll also find, especially in urban areas like where we are, your sewage lines are going to be in your lowest areas of elevation. Finally, what I'd like to point out is you don't actually have to see where the water is on a topographic map to know where there probably is water. And the trick to that is to look for where the contour lines V. So if you notice, in particular, where our study stream is, where Little Rock is, if you look up from Carthage Junior High School and you follow straight up, you'll notice that there are some V's on the contour lines there. Now, you can tell which way water is flowing on a topographic map because water always flows through the mouth of the V. And the way I always describe this to my students is I tell them to draw a Pac-Man around the V, and that kind of reminds them which way the water travels as it goes through it. So this is a 10-foot contour interval. You can see, not only can you tell which way water is flowing from going uphill to downhill, so you can look at the actual elevation, and you do have the index contours, like you'll see the 300 index contour at the top where the V's are that I'm mentioning here, that I'm talking about here. And so that's an index contour. It's going to be a slightly darker, bolder contour line. And that'll, in this case, it's every 50 feet is where they'll do an index contour. The contour interval is 10 feet. And then you can see how Little Rock, just to the left of that, it flows down through the mouths of those V's and then cuts to the east and then cuts south again, right past where we're going to be studying. Okay, so now it's your turn. Let's see if we can figure out the watershed for our study stream that we're going to be looking at today, which is Little Rock Creek. So find Little Rock Creek on your map, and what I would like for you to do is to highlight Little Rock Creek with your blue markers, and then to locate all of the highest areas on the map above and below. In this case, we've already mentioned how roadways tend to follow your ridge lines. So you can use the roads that are on this map to kind of assist you with that. Take a black marker or a black pen and highlight the ridge lines and just sort of connect them along the top and bottom of our watershed. Okay, see if you can figure out the direction that our watershed is going. So this is Little Rock Creek, and you see that it's going to kind of mirror the roads that you have going west to east here. So you're going to draw your line. It's going to come down, and it's going to come up and over the top of this stream, because your stream has to stay within the watershed boundary since it's flowing to this area. And then you're going to see this little, see these V's right here? So it's actually going to come down. Here, I'll take that, thank you. So it's actually going to come over and then come down and then come back up again. So anywhere that you see a V like this, it's going to have to probably go over the top of that, because if you think about it, that water, any rain that falls into this area is also going to drain down this way. So we want to include that into our divide. So we're going to kind of come up, and here's some hills. Here's a hill right here. Here's another hill, and then you got another little stream area here. So this would probably come up and over, and then hit this hill, and then there's another V. So it would probably kind of follow something like that. Very, very generally, that's another hilltop right there, so probably hit that. Okay? So it's not perfect, but you can see how the roads, because they have to make theirs as straight across as possible, but you can see how it would somewhat mimic. Here's a hill, here's a hill. So it would look something like that as you connected it. By creating this watershed, what we can do from this point on is we can actually start to look at the impacts and influences of Little Rock Creek. You may want to consider postponing the second half of Understanding Topographic Maps until you get to Module 4, which is entitled Impacts and Influences. And if you put it right before the activity, there's no point to this pollution and investigating your stream's drainage basin, you'll have a nice lead-in and an assessment for your students to work with. Okay, so for your classes, when you're doing this, the first thing you want to do is you want to go online and find a good colored topographic map. We used Acme Mapper for this one. And find your area, and then have your students do the same thing. You want to spread it out enough so that they can see ultimately where the stream will travel towards. And in our case, you can really see how it connects with Walnut Creek and then travels to the east and will eventually hit the Neuse River in this case. So this is a pretty good scale size for us to use. And have your students see if they can find all the ridge lines and create the divide for this particular watershed. Keeping in mind that watersheds can be as small as a pothole and be as large as a river basin.